I thought it'd be fun to make some Christmas arts and crafts while I was procrastinating on making a video about how I finally finished my PhD, but it kind of ended up being a lot more mathematical than I expected, and a bit of a nightmare, to be honest.
What is that? It's my calculator.
And then the thing is, it didn't even look nice in the end, but it was kind of fun in its own way, and so I decided to put this video up anyway. The thing with this video was that I wanted to start it without any plans about how I was going to do it in mind, because I thought that doing it that way would be more fun. And so you're going to see me make loads of mistakes and have to start again a few times.
Okay, so my idea is to make this into a cone, and then I'm going to add leaves that come out from the cone. So let's make the cone first. What I want to do is make these leaves coming off the tree like this, around the tree, but I need to decide how to space them. So what I'm going to do, I reckon, is have a spiral that goes around the tree and then place the leaves along that spiral. My first guess is that we could try and find out what the geodesics of this cone are. So a geodesic is a path on a curved surface that is locally flat. Say you wanted to get between 2 points on your cone. So here's point A and here's point B. Now you could go in a fairly direct manner, but what is the shortest route? What is the most direct route? Is it this straight line? Is it a slightly curved downwards line? Is it a slightly curved upwards line? We don't know. But how can you find out? Well, there's a theorem in geometry that the shortest path between 2 points is one that is locally flat. In other words, is a geodesic. Now, how can we find this locally flat path, and what does that even mean? Well, firstly, let's imagine that you are going to go on a path that is definitely not the shortest one. So let's say something like this. How can we tell that that's not locally flat? Well, if it was locally flat, then this piece of tape should sit flat on it. But instead, what we're going to see is we can't get the tape to sit flat. It's going to have to distort like this. To get between those 2 points. So that is definitely not a geodesic. Now, what happens if we do put a locally flat piece of tape between those two? So in other words, a piece of tape where the tape doesn't crinkle in either direction. So I'm going to hold it taut. Just, it's not quite the right angle. Gonna hold it taut. And here you go. That is the shortest path between those two things, and you can tell because this tape is sitting flat on it. So I'm going to use this tape as a guide to find this geodesic. You can see here that I haven't quite done this right because the tape is sort of sticking up here, and if you try and push it down, it doesn't quite sit flat. Now that is going to happen even if I was on the geodesic. This will only really work with like infinitely small tape, you know, in theory, mathematically, but it should be close enough, and so I think that I've actually got this slightly wrong. It should be more like, yeah. That there is more like a geodesic. So what I'm going to do now is I'm going to get some tape and I'm going to put it around this cone in a geodesic up to this point, and I'm going to see whether it actually does look nice or not. So do it like that. All right, now to get the geodesic, I have to pull this tape taut and then just see where it wants to land. Oof, got a bad feeling about this. This is a very tight spiral. It's almost overlapping when it comes around. Yeah, okay. So you can see here, ooh. You can see here that if I let it go where it wants to go, it actually, ooh, interesting. It actually comes back down. Oh, maybe the geodesic doesn't even go up this cone at all. Okay, let me test this. I assumed it would. I'm kind of surprised. Why did I assume that it would go up? I'm not sure. Okay, let's see. This is fun. It's like doing maths, but through experiments, like hands-on experiments, completely different from how I learned differential geometry in university. Okay, so what I'm gonna do is I'm gonna put it on a pretty steep angle and then see what happens. Okay. Oh, it's not likely flat there. Oh, that doesn't feel flat here. Okay, let's see. Okay, that's pretty flat. Yeah, it's looking good. Okay. Oh, looks like it's spiraling up. Okay. Oh, no. It's, yeah, it's coming back down. Interesting. Oh, wait. Let me see. I've stuffed this up a little bit. In fact, it goes back down even steeper. Wow, that's weird. Wow. This is weird. The line doesn't go up the cone at all. In fact, it goes up, as you can see here, and then changes its mind, kind of just goes in a circle for a bit, and then starts coming back down to end up here. That's really interesting. So, I was wrong. There is no geodesic that spirals up the cone, it seems. Let me verify that. Okay, so I've been thinking a bunch. I even got my whiteboard out and did a few little sketches. And here's what I'm thinking. Let's say that the spiral starts down here. I want it to come round and meet back at this line at some point up this length. So why don't I make that point that it comes back and meets this point like some fraction of the total length? I reckon a quarter. So I reckon it comes around once, ends up a quarter up the height. Then let's pretend as if the rest of the cone doesn't exist now, and we want to do the same procedure. We want to pretend that this is our new total length, and we want the next round of the spiral to come up 1/4 of this length, not the previous length. So then let's say that's about here. And then we do the process again. It's like, this is the new cone's length. We want the new point to be 1/4 of the way along that length. So it's about here, etc. Quarters are easy because you can find them pretty easily by just folding. So let's do that. Fold in half once, twice, then you tear off that little bit, and now you've got to find 1/4 of this new length. Etc. If you could do this accurately, there would be an infinite number of lines before you reach the actual top. We're going to stop before that happens because I don't have the time. You might be wondering why I chose this pattern. I wanted this tree to have a property called self-similarity. What that means is if you look at a smaller part of this tree, so For example, instead of looking at this full tree, if you cut it off at this point and you just looked at the smaller one, you would want that to look exactly proportional to the full tree. And the reason you can see that is because this full tree has its first spiral like wraparound coming back at this point, which is 1/4 up its full length. Whereas this smaller version of the tree has its first spiral coming up at this point, which is also 1/4 up the length of the tree, right? And so both of them will look exactly the same, just one is smaller than the other. I think that this will make it look a little bit more realistic, and I also think it will look really, really pretty. But let's find out. What I wanted to do was have these branches coming out of the tree arranged around the tree like this, but up the spiral, such that the one that ends up approximately here, so that is one step up the spiral, I want that to be 3/4 rather of the size of the one below. But the problem with this is that, well, because I have a cone here, the length thing isn't going to quite work out. Actually, this one's going to be a lot longer than 3/4 of this one, because this one is starting from a much further in point. So I think, even though it was a lot of effort to make this thing, I think I'm gonna have to start again with something more like a straw. Trees have this problem where they want to put out branches or leaves, but they want to make sure that the next leaves are not overlapping too much, because that would mean that there would have to be a lot of leaves to catch the same amount of sunlight, right? And so you want to avoid this problem. So the question is, if you put your first leaf down here, what angle should the next leaf be away from this leaf? For example, should it be like this? Apparently this is a question that has been studied before, and I don't know what the analysis is, but apparently the answer to this question is that this angle should be something called the golden angle. And yes, it is very related to the golden ratio, but I'm not going to explain what the golden ratio is, and I'm definitely not going to explain why this is the right answer. Instead, what we're going to do right now is we're going to see if visually this does seem about right. The golden angle is an irrational number, but it's approximately 138 degrees, which is very, very close to 3/8 of a full circle, which is convenient for us. So we're going to just assume that it is 3/8 of a full circle, and then go from there. The error is very, very small. So if our first leaf goes here, our second leaf should go 3/8 of the circle around, which is, so this is half of the circle, and that's 1/4, so that's 3/8. So it's here. That's where the next leaf would be. Next one after that is here. So you can see something really nice about this is that while there is little bits of overlap, so far there hasn't been any direct overlap, and yet this space has been filled very efficiently. Now this last petal, or rather last leaf, is going to go here. So that is some direct overlap. How many times around did we go before we got to this overlapping leaf? Well, it's 3 times, and the reason we know that is because each time we go around, we go 3/8 of the circle. So by the time we've gone 8 of these, we've gone around 3 times. But something that I've clearly gotten wrong here is that these petals don't get smaller in the right proportions. You can see how this one is huge compared to, well, everything else. And that's not quite right. That's definitely not how trees look. It is certainly the case that the leaves get smaller as they go up the tree, but not in this proportion. Alright, so let's figure out those proportions. So here's our tree trunk. Let's say that it has length L, capital L. If there was a leaf right at the bottom, or a branch, let's say with length little l, and then there was one here, what length should this one be? Well, so the point that we've gone up to here is 3/4 of L. Remember, we marked out these lengths this way because what we wanted was that if we chopped the tree here, what we would get is a miniature version of the full tree. It would just be shrunk down, so everything would be shrunk down by 3/4. The length would be 3/4 of the original, and also we want the leaves, the length of those leaves themselves, to also be 3/4 of the original. So this leaf that was at the bottom of the full tree should become a leaf here that's 3/4 of that length. So here it should be 3/4. The problem for us, though, is that if we have a leaf here of length L, the next leaf up the tree is not here, but in fact it's a golden ratio rotated along. So it's like here. Now, what length should this new leaf be? Well, let's think about it like this. If it had been here and it had rotated the whole way around, then it would be 3/4. But it's only now rotated 3/8 of the way. We need to figure out what this function is and then figure out what its value is 3/8 of the way between these 2 points. It so happens that this is actually a nice function and a very important one. It's called the exponential, although in this case it's exponential decrease. On this axis we're going to have the number of rotations, and on that axis we're going to have length of leaf. The first leaf has gone 0 rotations around the tree and its length is L. We know that if a leaf were to go around 1 full rotation, its length has to become 3/4 of L. But here, after 2 rotations, it has to be 3/4 of that. This function is exponential decrease. Our next leaf is 3/8 of a rotation. So we need to figure out what is this length. There's a nice way to do it. All we need to do is figure out what is the function for this thing. If we call the number of rotations x, then the length of a leaf that has gone around x rotations is 3/4 to the power of x times L. All we have to do is put in 3/8. That's 3 to the power of 4 to the power of 3/8 times L, which equals approximately, very, very close to 90% of L, which means that each successive leaf has to be 90% of the previous one, which is just awful. That is going to be a nightmare to be measuring out. Okay, I think that the best way to do it is to measure them all out in advance. So let's do that. Okay, but one thing I need to do is approximate how many I'll need in total. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, maybe 13 rotations that I want to do. Let's say 12, because that's nice. 12 is 4 lots of 3, and in 3 rotations we get 8 petals. So that means that we'll have around 8 times 3 petals or leaves or whatever it is in total. Oh my god, I'm tired. What is that? It's my calculator. 3, 8 times 3, 24 apparently. Okay, I'm gonna make 24 leaves, each one having 90% of the length of the previous one. Okay, so I went ahead and measured out the lengths up until 17, then they just kind of get really small, so I don't think it matters too much. But now I have to make those branches or leaves. So what I've decided to do is I've got this piece of paper, I've folded it in half because the longest of these is about half of the paper. Then what I'm going to do, hopefully successfully, is make a bunch of triangles out of this paper that are all isosceles, and then I will trim them down to these lengths. Let's say this is my first leaf and I want the second one to be 90% of the length of that original one. I could make it 90% of the length by cutting it here, but I also want it to be 90% of the width. In other words, I just want it to be this actual triangle, but all of the dimensions scaled down 90%. Then actually just cutting it will do that. And that's because you can see that this, if I was to cut it, say here, the angles are still the same. This angle and this angle are the same, and these two angles are still the same. And so it is still a congruent triangle, and therefore these two will be the same as each other, just scaled down in both dimensions. Okay, there you have it. The exponential decay function as a bunch of leaves. Oh, that is badly off. I decided that I'm going to stick the rest on with the hot glue gun because this is looking really trash right now, and I want to see if it's gonna keep looking like that when I stick everything on and it's not flopping around. So yeah, let me do that. Alright, what I need to decide is what to do about this top, because I could keep adding leaves and that would be fine, except it's gonna be a lot more leaves to fill this. You can see that these lines are getting very, very close together, and it's kind of tedious to make these like very little leaves. But then what happens to that top section? What I was hoping was that the sort of nearer to the top leaves would be big enough to kind of curl over the top, so that you wouldn't need to worry about the like infinite number of leaves that should be there. But what I didn't take into account is that, of course, the length of these leaves is getting smaller proportionally, and so that isn't going to happen. Alright, so this is the final product, and as you can see, what I did for the top was I just added a cone there instead with the right height. I think this is actually kind of a fair way to finish this off, because it does have the right sort of proportion. For this to actually work, the whole thing should be a cone, and so I should, you know, try and make sure that this cone has the right sort of angle as the rest, but I really can't be bothered, so whatever. Anyway, you can see that this tree kind of looks alright from above, but from the side you can see just how sparse it is, so it doesn't look great. And the thing that really went wrong there is a constant that I picked right near the start. There's only one variable that I chose for this tree, and it was how quickly the leaves would spiral around. So if you remember, I chose it so that the leaves would go around once by the time they got up a quarter of the tree. So then if I were to cut off the tree there, then the next round of leaves would go up once by the time they get up to the quarter of the new tree. And so that was the variable that I chose. And clearly it was way too big. Like, there needs to be far, far more leaves before the tree gets up 1/4. At the moment there's only 3. So I really hadn't thought about that, and if you are going to do a similar project to this, I recommend you pick a much smaller number than that, which is a little bit of a pain because it means that you're going to be putting on a lot of leaves, but I guess that's the price to pay if you want it to look pretty. If you don't care about it looking pretty, you can just do what I did. Voila. Alright, I think I'm gonna call it a day. It's actually been 3 days that I've been working on this tree, and I'm tired and I don't want to do any arts and crafts for a while. Thanks for watching.